Hello, I'm Michael Brown, and I'll be presenting our work on understanding and mitigating the negative impacts of compiler optimizations on code reuse gadget sets. Compiler optimizations are primarily concerned with the performance and correctness of the code they produce. Unfortunately, the security impacts of optimization design choices are difficult to determine and even more difficult to quantify. Historically, this has led to several instances where compiler optimizations that have been proven correct have introduced security weaknesses into programs. A classic example is depicted at the bottom of the slide, in which dead store elimination optimizations in compilers remove program-replaced key sanitization code. Our motivation in this work stems from our prior work on software debloating, where we discovered that even small changes to programs, such as removing inconsequential or peripheral features, can result in large changes to code reuse gadget populations, to include the introduction of new gadgets. This has led us to question what the effect of compiler optimizations are on code reuse gadget populations. And to answer this question, we started by conducting a broad study of optimization behaviors to determine if they're improving the quality of code reuse gadget sets and making the job of an attacker easier. Specifically, we seek to answer the following 6 motivating questions. In the interest of time, I'm not going to read these now, but we will cover them on later slides. Before we get into the details of our study, I'd like to take a moment to review some terminology and explain a simple gadget-based code reuse attack, in this case, a ROP exploit. First, gadgets are snippets of the target program's code that are used by the attacker to create exploits. Specifically, the attacker will exploit a memory corruption vulnerability and write a chain of gadget locations and data to the stack, and then they'll redirect execution to it. In the case you see on the right-hand side of the slide, the first 3 gadgets pop attackers' data from the stack into the EAX through EDX registers. The 4th gadget is a special purpose gadget that executes a system call using these registers as parameters. Ultimately, the end result of this simple exploit is the opening of a shell for the attacker. To thoroughly study compiler optimization behaviors and how they impact code reuse gadget sets, we built a large dataset of over 1,100 variants of 20 different benchmark programs. These benchmark programs are sourced both from the Spec 2006 benchmark set as well as a number of common Linux programs. We built our variants using 2 production compilers, GCC and Clang, and we built these variants to support 2 types of analysis. The first is coarse-grained analysis, which compares code produced at optimization levels 01, 02, and 03 to unoptimized code produced at level 00. The second is fine-grained analysis, which isolates the behavior of single optimizations for analysis. To analyze the gadget sets in our variants, we use a tool called GSA, or the Gadget Set Analyzer. It performs a number of functions to include cataloging the various types of gadgets in the binary, filtering out gadgets that aren't suitable for chaining, and qualitatively and quantitatively analyzing the set of gadgets. But most importantly, it allows us to compare sets from different binaries. Specifically, GSA computes 4 metrics of interest to our work. The first is gadget introduction rate, which measures the percentage of gadgets in optimized code that are not present in unoptimized code. Second, it calculates gadget set expressivity, which is a measure of the computational power of a gadget set. Third, it calculates gadget set quality, which is a measure of the composability of the gadgets in a set. And finally, it measures the types of special purpose gadgets that are available to an attacker. Without further ado, let's begin to answer some of our motivating questions, the first of which is, to what degree do compiler optimizations introduce new gadgets into optimized code? Examining gadget introduction rate information across our coarse-grained variants revealed that more than 2/3 of the gadgets in optimized code produced at levels 01, 02, and 03 were newly introduced versus gadgets in variants produced at level 00. Across our fine-grained variants, we observed that the average gadget introduction rate was approximately 25% for a single optimization in GCC-produced binaries, but was a striking 82% for a single optimization produced in Clang binaries. Ultimately, our analysis allows us to conclude that compiler optimizations, individually and collectively, cause massive changes to gadget set composition. Next, let's take a look at our second motivating question, which is, to what degree do compiler optimizations negatively impact the security of optimized code with respect to code reuse gadget sets? Across our coarse-grained variants, we observed that optimization increases the expressive power, average quality, and size of gadget sets in a large majority of variants. Further, in a large percentage of variants, these increases were quite significant, approximately 37% with respect to expressivity and approximately 74% with respect to quality. Special purpose gadget populations, on the other hand, were not as significantly impacted. We observed introductions in approximately 33% of variants. However, we also observed a total reduction in the number of gadget types available in 28% of variants. When we examined our fine-grained variants, we observed low-grade increases across all of our qualitative gadget set metrics, across all benchmarks, optimizations, and compilers. This manifested typically as an approximate 5% increase in the number of quality gadgets, small increases in gadget set quality, and the introduction of one type of special purpose gadget or less. Within this ubiquitous background noise, we also observed a number of large magnitude impacts over several different optimization types. This leads us to answer our next motivating question, which is, which specific optimization behaviors are causing negative security impacts? To separate this signal from the background noise in our fine-grained analysis, we performed outlier detection across our fine-grained variants, and ultimately we identified 5 specific optimizations that frequently cause large changes in our gadget set metrics. 4 are included in GCC: interprocedural constant propagation function cloning, jump following common subexpression elimination, peephole optimizations, and the omit frame pointer optimization. One problematic optimization was discovered in Clang, which is tail call elimination. Knowing which specific optimizations are demonstrating undesirable behaviors, we can now begin to answer our 4th and 5th motivating questions, which are, what are the root causes of these negative security impacts, and how can they be mitigated? To identify the root causes of these phenomenon, we performed differential binary analysis on our single optimization variants using IDAPRO and BinDiff. We focused on the specific optimizations that we highlighted prior. However, we also examined a representative sample of other variants and baselines. The first root cause we'll examine is the duplication of gadget producing instructions, or GPIs. We observed that several optimizations eliminate unnecessary instructions and function epilogues preceding GPIs. In this particular example, this is the return instruction in the red box indicated at the bottom of the screen. If the function epilogue is targeted by multiple predecessor blocks, after the instructions are eliminated, the GPI is duplicated and hoisted to the end of each predecessor block in order to save a small amount of code space and the execution of a direct jump. Unfortunately, this results in a large increase in the number of unintended gadgets, because each GPI is a termination point for multiple gadgets that can be interpreted by the stream of bytes preceding each GPI. In formulating a mitigation strategy for this problem, we observe that the GPI hoisting and duplication behavior is a secondary optimization, and thus we can mitigate by changing code generation and optimization behavior to avoid this secondary optimization while obtaining the benefits of the primary optimization, which is eliminating unnecessary instructions and function epilogues. However, we can generalize this a bit into a guiding principle in which each function generated by the compiler should not contain more than one instance of a particular GPI. If we merge them together and use direct jumps where appropriate, we can greatly reduce the total number of gadgets produced per function. The next root cause we'll examine is transformation-induced gadget introduction. In general, transformation behaviors employed by compiler optimizations both directly and indirectly induce churn in gadget populations. This phenomenon is documented in our prior work and ultimately is the cause of the background noise we observed in our fine-grained analysis. This effect is most apparent in code layout changes that occur after optimization, such as the example you see at the bottom of the slide. In this case, after optimization, the code on the left is significantly shortened and reordered into the code you see on the right. This change in code layout results in an update of the displacement for the conditional jump at the end of this basic block. In this particular case, the new basic block displacement encoding contains the byte C3, which, if interpreted in an unaligned manner, is a GPI for the return instruction. Ultimately, this means this displacement can now be used as a GPI and thus introduces new gadgets into the program. Unfortunately, this root cause is machine dependent and endemic to the x86 ISA. Thus, this is not something we can directly mitigate by changes to compiler optimization behavior, as these optimizations are typically made in a machine independent manner. Ultimately, to mitigate these issues, we need to employ gadget-aware compiler backends that avoid unintended GPI encodings during code layout. The last root cause we'll examine is special purpose gadgets that are introduced explicitly by optimization. Clang's tail call elimination optimization will replace tail calls with tail jumps where possible to eliminate stack frame setup operations. When this tail call is an indirect call, the result is a JOP data loader gadget that is introduced into the code, which performs this function. Unfortunately, the transformation itself in this case is explicitly creating a particularly useful gadget. This optimization behavior cannot be decoupled from the negative gadget set impact. In order to mitigate this problem, really all we can do is try turning the optimization off. This strategy is one that has been used prior with optimizations that are problematic, such as dead store elimination. However, these are subject to a performance trade-off. It's also worth noting in this case that many programs cannot be built with tail call elimination disabled. To assess our mitigation strategies for GPI duplication and transformation-induced gadget introduction, we built 5 gadget eliminating passes for Egalito, which is a binary recompiler tool that enables transformation on machine-dependent IR. Specifically, our passes merge duplicated GPIs, eliminate layout-based gadgets via NOP sleds, and perform whole program function reordering to eliminate GPI encodings and call displacements. We then recompiled our GCC and Clang 03 variants with Egalito and our mitigation passes enabled. We discovered that our passes are quite effective at reducing gadget set quality and size. In particular, our mitigation passes reduce the total number of special purpose gadget types in 74% of variants, and in most cases by more than one type. On average, our passes eliminated 31.8% of quality gadgets in gadget sets and reduced the expressive power of gadget sets in approximately 78% of variants. However, we are left with one final motivating question, which is, what is the performance cost of implementing our mitigations? To answer this question, we compared the performance of our recompiled variants against their respective 03 and 00 variants. And we observed an average speedup of 0.2% across our Spec 2006 benchmark programs. While this may seem surprising at first, it's actually to be expected, as Egalito's core recompilation process has been shown to achieve a 1.7% speedup on average. To assess our mitigation strategy for special purpose gadgets that are explicitly introduced by optimizations, in this case Clang's TCE optimization, we evaluated the performance impact of disabling this optimization. We observed a striking 14% average slowdown for binaries with TCE disabled produced by Clang, and ultimately this performance impact outweighs the security benefits of preventing JOP data loader gadgets from being introduced into programs. To conclude, I'd like to summarize a few key takeaways from our research. The first is that compiler optimizations individually and collectively cause massive changes to gadget set composition, and avoiding increases in gadget set quality is not as simple as selecting a particular optimization level or turning off problematic transforms. But fortunately, there's hope in that compilers and recompilers, in our case, can mitigate these effects via simple transformations that don't impact performance. However, it is worth noting in some cases, trade-offs must be made. And with that, we thank you for listening to our talk.